So till now, we have learned about the interaction of atomic systems with background quantum field, and we have seen that the quantum fluctuations are sometimes capable of doing strange things. And in principle, if a finite time duration operation, one can cause the atom to get into excited state if it initially starts in the ground state. However, for long time duration, what we have learned that the presence of photon of the same frequency is required to undergo a transition from the ground state to the excited state. From this class onwards, we will look about the reverse phenomena of that, which goes by the name of spontaneous emission, in which an atom is initially in the excited state of the Hamiltonian, and since it is eigenstate of the Hamiltonian, it is in principle supposed to live there forever unless perturbed. So what we will see that if the atom talks to the background quantum field, the quantum fluctuations within the quantum fields are strong enough to cause a downward transitions even if the state of the quantum field happens to be the vacuum. So just like what we had discussed, there was a probability of up transitions previously due to the quantum fluctuations in the background. There is also a reverse probability of getting down. Up probability was a proportional to delta function of energy gap divided by h bar minus omega k plus omega k naught plus omega k. This kind of expression was obtained for large time operation. For finite time operation, it was replaced by some sine function, which was small but non-zero. Now we are going to talk about what would happen if the atom initially starts in the excited state and where does it land after a finite time as well as a long time. Okay. So the premise is this thing that initially that both the ground as well as the excited state are the eigenstate of the unperturbed Hamiltonian. So I have a statement that H naught acting on the ground or the excited state are going to give me the state back and with their corresponding eigenvalues of the energy. So in principle, they would live there if they are unperturbed. The electrons in the system or the atom collectively would live in those states forever, and they will never change to their another state because these are steady states. However, the statement is due to coupling of the background field, there can be some new correction term which we have seen, and that will cause the transition downwards or upwards which we have computed. So again, for demonstration purpose, we will start with a monopole coupling where a scalar field phi is talking to the atom through a monopole operator term m. Now we have defined that the atom is going to be in the ground state, in the excited state to begin with, and the background field is in the vacuum state. The background field is in the vacuum state, that means its expectation value is 0. However, we have seen while we were discussing the quantum field theory structure that despite the expectation value of the field operator being 0, the 2-point correlator does not become 0 for even for the ground state of the quantum field, even for the vacuum of the quantum field. So therefore, there are inbuilt tiny quantum fluctuations coming from these quantum correlators which are present, and these small fluctuations which pop up in very small amount of time and disappear, pair production happens and disappear, that makes the system dynamic, and therefore there is a time dependent perturbation which turns on and off repeatedly again and again, and that causes the atom to come down. And we will compute the probability of that just like we had computed the probability of the atom going up. Only thing would be that the systems will change from the initial state will now be excited state of the atom. Previously we had computed things of probability of going from the ground state of atom while the quantum field is in vacuum state to ground, the atom goes to the excited state and the field goes to some state psi which we later on sum over. And that expression was given by this integral mod squared, where the interaction Hamiltonian was squeezed between the states of interest. For this consideration, where we are considering a reverse phenomena, our excited state is the initial state. That means atom will start in the excited state, the field will still remain in the vacuum, and then we are asking for the probability that the atom goes to the ground state and field goes to some physical state psi, which we will sum over later on. So this time the operator of interest, the interaction Hamiltonian interaction term will be squeezed between E0 and G psi. Previously it was being squeezed between G0 and E psi. Okay, so this is the reversal which will happen. So now we have to compute this time integral and its mod square rather than the previous one. Structure wise, it is not going to be much different. We will just pay attention where do these things appear. So recall when we were doing the computation, the when we were doing the computation for excitation, this monopole operator was getting squeezed between the excited and the ground state in complex conjugate pairs, while their exponentials were coming with e to the power plus iota delta e upon h bar times t prime and minus delta e upon t double prime upon h bar. This time the role is reversed. Initial state is E, excited, of the atom. Final state is G. This is what we want for the atom, that the probability that a transition from excited to ground happens. Previously, the reverse was happening. This side the G was sitting and this side the E was sitting. And that's how a plus iota was coming about in the exponential. This time a minus iota is coming about. So if you are just careful about the appearance of a state in the correct order in the bracket notation, you will just realize it is almost the same computation, only for the fact that the exponentials argument will become a plus iota delta E upon h bar t minus t prime. Previously it was a minus iota, this time it becomes a plus iota. This is because the flipping of role. Initial state is excited and final state is the ground. The previous time it was the other way. The initial state was ground and the final state was the excited. And that's why this change of delta E signature comes about. Other things remain exactly the same, and you do get the phi, the field operator, squeezed between 0 and psi and 0 like before. That does not change. The order, that because the field state, remember initially also we were asking for the field to go from the vacuum to the psi. Only interesting thing was happening for the atomic system, it was going from ground to excited. This time the role of the atomic system has changed. The field is doing the same business. It is going from the vacuum to some psi, and the mod square of that would give me a complex conjugate version of this squeezing, this matrix element. So ultimately in the field side nothing changes. In the atomic side a plus iota delta E appears in the expression. Okay. And as before, if we are interested in just the de-excitation of atom only without caring about what happens to the field, what we will do, we will sum over all the possible field state. This psi which appears over here, if I sum over all possible Fock space basis elements, then this gives me just the projection operator of identity. So like before, if I sum over all the field, final field state where the field can go, all the good bases into which the field can be decomposed into, the probability of only information of only the field, the atom goes from excited to the ground state, is obtainable from this psi projection summed over all psi, which is nothing but the identity. And as a result, I will again get, it is yet again the 2-point function of the field, this time undergoing the same Fourier kind of transform with a positive iota delta E. Last time it was a minus iota delta E, if you remember. Therefore, it is almost the same computation but with a sign flip. So we will do that and we will see again like before, it is going to give me the probability of down transition. Previously we were computing the up transition probability, and this time if it survives, it is happening solely due to the quantum field 2-point correlator, quantum fluctuations in the vacuum state. That is the source of this down transition if it is non-zero. Previously, when there was a minus iota over here, this integration over long time interval became 0 because of positive argument of delta function. You can now anticipate, since the sign of the delta E has flipped, this time I am going to get a delta function which is not necessarily positive argument. That's why it is going to survive. So therefore, there is a vacuum structure of the field which is going to cause a de-excitation, and this goes by the name of a spontaneous emission. That means atom will undergo a de-excitation, it will emit a photon, and this is spontaneous. It is not caused by any active agent. You are not supplying anything to the system. Only the quantum fluctuations of the background field are sufficient to do that. All right. So this is the genesis of a spontaneous emission. This, you can't help it. This quantum fields always come with fluctuation. This is not under our control. This is no parameter where we can control and increase or decrease this. So this is a basic inherent nature of a quantum fields. It comes with a quantum 2-point correlator and quantum fluctuation, and no matter what, this is always going to be present, and therefore it will cause an emission of the atom on its own. So therefore the name is spontaneous. Nothing has to be done. This is spontaneous emission. So we go ahead and try to compute this expression. As before, we know that the 2-point function can be written for atoms at rest like this: e to the power minus I omega k t minus t prime. Remember, the 2-point function was truly e to the power minus, rather plus iota k dot x minus x prime. And when I open it up, I would get a t minus t prime with a omega with a minus sign, and plus iota k vector dot x position x minus x prime. So if atom is at rest, then x and x primes are the same quantity, in the spatial locations are the same. So they will just go away from this exponential, and I will only be left with this temporal part in the exponential. So the 2-point function is just this. What I have to do, I have to take this 2-point function and supply it back into the expression over here. And as a result, I get the probability of down transition as this simple integral. So I have a 1 d3k integral to compute of this exponential omega t minus t prime, and another exponential with t minus t prime in the its argument also appears. So I will combine these like before, and we will evaluate the 2-point correlators integral transform. So as we have done so many times by now, I will collect all the t functions at one place, undergo the temporal derivative. So I will take this dt, this first exponential's time dependency, and this second exponential's t dependency together, and I will get some structure like this. So see, what do I get? First exponential has a plus iota delta e upon h bar. So I get plus iota delta e upon h bar, and then e to the power minus I omega kt, which is coming from here. Let me erase it out so that we can see it with clarity. That e to the power minus I omega kt comes over here. So I combine it in the argument of exponential. So this is the whole t dependency in the whole integrals, and that undergoes with a time integral of dt. Similarly, for dt prime, you can collect this and that together, and I will have this second integral over here, which if you pay attention again is the similar thing like complex conjugate of each other, but for the fact this is computed at time t, and while this second integral is computed at time t prime. This was the same thing which we had seen before as well. Only thing which has changed this time is that the signature of the exponential has slightly shifted in the delta e. Again, like before, I know how to compute this exponentials. You do this exercise because we have done it before, and you will be getting the same integral from both the sides, not exactly same, but up to a complex conjugate phases of each other. So overall, you are going to get 2 sine delta e upon h bar minus omega k t by 2 and divided by delta e upon h bar minus omega k by 2 whole square. So this is the simple integral. You can see that this goes, so this, the first integral goes into sine the whole thing with some phase, and the second thing goes the whole thing again with the opposite of the phase. So ultimately only the magnitude square survives. Phases cancel out from these integrals. This is a simple exercise you should try because we have done it before. Previously, if you recall, we were getting a plus here. There was no minus, and here also there was a plus. So therefore I was getting plus here and plus here as well. Not this time. This time I have a sign difference. So you see, in the large time limit, in the large time range of this integral what we are discussing, we are going to get a delta function which can survive this time. I will get a delta of delta e upon h bar minus omega k by 2. So I have done the simple opening up of the integral. This d3k, if you remember, was going to give me 4 pi k square dk. For massless field, k and omega k are the same thing, so I cancel 1 power of k square dk with k dk will survive. 4 pi will come about, and there is a this sign in the large time limit gives me a 2 pi of this delta function as well. So overall 2 pi cube would come about, and I will get an extra 2 because there was, remember, there was a 4 pi k dk. So this is a simple exercise what you should try to do and verify for yourself. Indeed, you are going to get in the large time limit this integral. So now you see I have a delta function which is not necessarily positive definite argument. Previously, when we were looking for up transition for long time limit, the delta function earned up an argument which was totally positive, hence it was 0. This time it will not be 0. Remember, there is an integral going on. So integral is changing the omega k continuously because this is a running integral in k. So at one time, the k value will be such that omega k for massless field, remember, it is nothing but k times c. So c is equal to 1 unit, it is just k. So one particular value of k will satisfy the argument of the delta function, and there it will survive. Previously, when it was plus, no running value of k would make the argument of delta function 0, because k is running from 0 to infinity and the argument of delta function was positive throughout and it was vanishing. This time it will survive. So you can see, you evaluate it as a delta function, split the two delta function, delta e upon h bar minus omega k, and another copy of that, delta e upon h bar minus omega k. Now you treat this as a function fk and use this as a delta function. Do this integral. The result will be, it will take f of 0. F of 0 is delta 0. This k over here will take the value of delta e upon h bar up to a c. I am putting c is equal to 1 unit. You should be very careful about that as well. So you see, ultimately I am going to get a result which is going to be this matrix element mod square divided by h bar square. This 2 pi cube exactly cancel with this 2 pi cube, and delta e upon h bar survives. So now there is a non-zero probability of down transition. This is the spontaneous transition probability, and this depends on the matrix element mod square and delta e upon h bar. That means if I increase the gap, delta e upon h bar becomes large. That means the separation between the ground and excited state is large. Then the probability becomes high. So therefore, larger the gap, it is more easy for the vacuum fluctuations to knock the atom down. The quantum fluctuations will find it easy to mediate between larger energy gap states so that it can come down. For smaller energy gap, this probability is slightly less. This is counterintuitive, because one could have thought that vacuum fluctuation should not be too much of energetic things, so they should cause transitions across low energy regime. But no, combined with the density, remember, this delta e upon h bar is surviving because one of the delta functions substituted the value k over here into delta e upon h bar. So the reminiscence of this thing, which was initially 4 pi k square dk, and that 1 power of k was cancelled by the 2 omega k in the denominator. But anyway, this is the survival of the density of modes. So density of modes gets increasing and with k. So therefore, 1 power of k survives, and that is the reminiscence where the delta e upon h bar survives. Despite being low energetic stuff, vacuum fluctuations do not come up with very large frequencies. But even then, at large frequencies, the number of such modes are large, and therefore the density times small probability becomes a larger winning function, and therefore it becomes easier for vacuum fluctuations to knock the atom down. Okay, so this is one interesting prediction, that I take highly separated states. If I do nothing to the atom, even then the atom would more occasionally be found in the ground state rather than excited state, because quantum fluctuation would not leave it alone to remain in the excited state. We would have thought from standard quantum mechanics, excited state is eigenstate of Hamiltonian, so atoms should live there forever. Not this time. Quantum fields effects, despite the field being in vacuum, causes a down transition definitively, and larger the energy gap, larger is the probability of transition. So therefore, we have to be alert about the fact that there is always a down transition probability, which is the spontaneous. So now we have seen a toy model in which a scalar field phi was talking to an atom through a monopole coupling term m. But in more realistic settings, we would have a more general, well-known field like electromagnetic field, which will be talking to atom through its, let us say, dipole coupling. The interaction term would not be m phi, which was just a technology demonstrator Hamiltonian. A realistic situation could be one of the case where the dipole moment of atom talks to the background electric field d dot e. So this term would be mediating the transitions, and let us estimate, going along the same lines, that what would be the down transition probability for this realistic interaction. So you do the same steps what we have done for monopole coupling. The same step we have to repeat. Only thing one has to be careful that instead of m, a vector d will come, and instead of phi, a vector e will come about. So when we were getting the squeezing element m between the initial state which was excited and final state which was g, this time a dipole operator will sit over there, and when I do go for a complex conjugate of that, the complex conjugate of the same operator, but this time with a different index. Remember, the D appearing here is getting dotted with the E appearing over here. And similarly, when I do a mod square, the complex conjugate, the D appearing here should get a dotted with the E appearing over here. So previously I was getting a 2 copies of MEG and let us say EMG, and inside the integral I was getting 0, 5 of t and 5 of t prime. The realistic version of that is that this m and this 5 were coming together and this m and this 5 were coming together. So this time the same thing structure will happen. The D and this E will come together and this D and this E will come together. Okay, so you will be able to write down the probability of transition like this. All right. So now we already know in the Lorentz gauge quantization of electromagnetic field, we can write down A0 to be 0, and therefore the electric field will be just the temporal derivative of the spatial 4 vector, the vector potential AI. Okay, and we have already seen the quantization of AI and whatnot. So I'm just going to recast the results which we have already seen before. The 2-point function of the vector potential, the different component of vector potential, AI and AJ, could be written like this. This exercise we have done. So this is just I have just copied it from our earlier discussion. This is the same slides which you have already seen. Go back to the lecture notes over there or go back to the lecture videos and do verify. This is just copied from the expression which we have already seen. The 2-point function between the two A's, two vector potentials, AI and AJ, can be given as GIJ. The name can be given to GIJ. And its expression is almost like the scalar field. Scalar field would have just this, but because of there is a gauge condition which we had discussed about and there are vector potentials which we are talking about, it should come with index I and j, and the gauge conditions which we were using, that it is a transverse field, it has no component along the direction of propagator, enforces the delta function to be modified by delta ij minus pi pj upon p square. Remember, this is just a projector operator in the orthogonal. This was for the vector potential AI and AJ. What we need is the electric field EI, EJ. You can take the temporal derivatives of these quantities as we have done before and obtain the electric field 2-point correlator. So using all this again is nothing new. You have already seen that and we have done that already. You just do the temporal derivative of each of the A's appearing in the expression. That means first I will take the temporal derivative of this A and then I will do a temporal derivative of this A. The result will be the extra iota omega factors which will be thrown out. Okay. So the two A's will give me the two extra iota omega, one with level P and one with level P primed. One from this derivative and one from this derivative, which will come out. Again, we have seen it before and you know the results already. The 2-point functions of the vector potential, the 2-point function of the vector potential can be converted into 2-point functions of the vector electric field like this. This is almost the same, but with the fact that here extra omega p square comes about, which takes the omega p in the down to the upstairs case. This is the simple thing. Okay, remember there was a delta 3 pp prime will come about because of the operator A and A daggers surviving only for this pair. And that will convert the p prime into p and therefore the omega p will be uplifted. So the 2-point function of electric field component is this. This we have seen before. So you go ahead, you compute this integral this time. So I have this extra factor which has come and sit in our place. For a scalar field, this extra factor was not there. The scalar field, only this integral I was interested about for atom at rest. Again, the same game. I am talking about atom at rest. That means the spatial locations are not changing. So k dot x minus x prime is going to become 0, the spatial part of that. So only temporal part will survive. So therefore, I have to just do the same computation one more time, but for the fact that one has to be alert about this presence of an extra term, which is handy. All right. So in order to do that, I have to just be careful about a couple of things and then we will be done because this is nothing serious integral. Its base structure is very similar to what we have done. So let us focus on the second term first, the second extra term. Let us say this term. I have a ki kj integral and there is a d3k integral I have to do. d3k integral means dkx, dky, dkz, the three-dimensional spatial integral. Now omega k depends on the magnitude of kx, ky, kz, as in omega k is magnitude of vector k, which is square root of kx square plus ky square plus kz square. That means it is an even function of kx or ky or kz. The magnitude mod k square is also an even function of kx, ky and kz. And last k dependency is also here in terms of omega k, which is also an even function of kx, ky, kz. So that means as long as I and j are different numbers, suppose I am computing k1, k2. k1, k2 is meaning kx, ky. So that means I will have an integral which is dkx, dky, dkz, even function of kx, ky, kz, even function of kx, ky, kz, even functions of kx, ky, kz. Only a single appearance of kx here and a single appearance of ky over here. That means I will overall have an odd function under symmetric integral. Remember, in d3k, kx, ky, kz all are running from minus infinity to plus infinity. So as long as I and j are different quantities, they can be separated out in terms of their integrals, and therefore it will become an odd integral, odd function under symmetric integral that will vanish. So therefore, this second term can only survive when I is equal to j. Okay. So therefore, I can write down the integral, which is the second piece, this piece, d3k upon about 2, forget about the 2, d3k omega k times ki kj divided by mod k square times this e to the power minus I omega k, t minus t prime, that I have written over here. This can become non-zero only when I is equal to j, and when I becomes j, it becomes ki square or kj square. So this condition can be written as ki square times delta ij. Okay, so now you see both the terms are proportional to delta ij. First term was anyway proportional to delta ij. Second term by operational means we can show that it is only proportional to delta ij. So that means I can pull out a delta ij as a common thing. Then the first term in the whole expression over here becomes 1. Delta ij has been pulled out. Second term is delta ij divided by mod k square multiplied by ki square. So I'm going to write as 1 minus ki square k square. Okay, this is fine. Now you can further realize, if I pay attention for this integral. If I look for this integral, I have a d3k by 2, I have a omega k, I have a ki square upon k square, and then this delta function square. Again, remember the t and t prime integral. This integral we have already done for vacuum fluctuation, kind of the spontaneous emission case. So for scalar field, this is the same integral. So this is again going to give me a delta function squared. Now you pay attention that this ki square, I can take value 1, 2 or 3. If it is kx square, then that means I have a dkx, dky, dkz. So dky, dkz integrals will be done, but kx integral is kx square and the symmetric functions of that running from minus infinity to plus infinity. Had it been a ky square, then also the same integral is being performed. One quantity ky square running from minus infinity to infinity, and similarly for kz. So that means what is appearing over here, ki square, k upon k square, is same for all I. If it is kx square upon k mod k square, then also the integral result is the same. If it is ky square upon k square, then also the result is same, and similarly for kz square. That means this together is ki square. The integral's value can be added together, then it will become kx square plus ky square plus kz square. That means that is 3 times 1 of the ki square. So if I add it together, then the operational part is k1 square plus k2 square plus k3 square divided by k square, and that should be equal to 3 times the same integral with kx square, because ky square, kz square integral should be the same. So that means just the kx square integral is 1/3 of this integral. And remember, kx square, ky square plus kz square divided by k square is just the k square itself. So this will cancel out. So that means I can write instead of this 1/3. So that's what we do. If I write for ki square upon k square as 1/3, That means the integral which we went after, 1 minus ki square upon k square, is 1 minus 1 by 3. That is to say, it is just 2 by 3. So I have the same integral, delta Ej has been pulled out, 2 by 3 over here, and you have to do this delta function integral, which is very trivial to do. This time d3k integral will again give me 4 pi k square dk. Remember, for scalar field there was a denominator omega k which reduced the power of k by 1. This time for electric field, omega k is in the numerator, so it multiplies to the power of 1. So k square here becomes k cube, and the delta function becomes delta E upon h bar to the power 3. For scalar field, it was delta E upon h bar to the power 1. So you see, for realistic case, the probability of transition is cubically proportional to the frequency for vector field, for the electromagnetic field. So this is one of the robust results, that the atomic spontaneous emission for realistic settings is cubically dependent on the frequency gap. It reacts very vigorously for high energy separation. Previously, for a scalar field, we had seen that the probability goes linearly proportional to the energy gap. This time it is going third power to the energy gap. That means it is even more possible for the vacuum fluctuation to knock down the electron if it is in excited state, more and more higher excited state. So vacuum fluctuations for electromagnetic field are much more powerful than the vacuum fluctuations of the scalar field. So you get this probability of transition rate, this probability of transition from the excited to the ground state. This is the spontaneous emission probability. A delta 0 comes about for the long time operation. Remember, long time operation here again means larger than any internal time scale, but smaller than the time scale over which perturbation theory will break down. That means this is the total time of operation where the perturbation theory approach works about. It is not a real time infinity. So if I divide by that time or take a derivative with respect to that time, I will get a rate which is this. The rate is also cubically proportional to the atomic energy gap. This is one of the famous results of the spontaneous emission for realistic system, that the frequency proportionality, cubic frequency proportionality, is a hallmark of a spontaneous emission for atomic system. Most of the atoms interact very strongly with electromagnetic field, and a cubical spontaneous emission rate is a fundamental result which one is always looking for. That this has been realized in the lab settings in many experiments as well, but this is one of the hallmark signature or hallmark prediction of a quantum fluctuation, that there is a tendency of down transition with a cubic frequency dependency. All right. So that was for the vacuum part. Now suppose we want to know about the process, what happens if the field comes up with a photon. So instead of being vacuous, if the field is in some excited state, let's say 1 k naught or 1 photon of a frequency k naught is present, what happens to the de-excitation? If the de-excitation is assisted with the presence of a photon, the process is known as the stimulated emission. In this case, we have to know the process probability, that when the initial state of the field is 1 k naught and not vacuum, what is the down transition probability of the atom? Again, the process which we are asking for, the initially atom is in excited state, field is in 1 k naught state, and then after the process end, the atom goes to the ground state and the field goes to anywhere it likes, psi, which we will sum over. So this sum over all the Fock basis element, all the good state of the Fock basis are summed over, then it becomes a projection operator as we have seen. And the probability of down transition takes this form, where now the phi t and phi t prime gets squeezed between initial state and the final state psi, and final state and the initial state psi, and then the psi is summed over. So this is just the identity operator over here. The psi, outer product psi psi, is just the projector operator of the full Fock basis element, which is just identity. So therefore we will get the 2-point function of the field between the initial state of the field, which is 1 k naught this time. This is exactly the same result which we had obtained for the case of absorption as well. Only thing, if you could notice, is the sign change of delta E which is coming about, which is exactly coming from this term where the initial state is excited and the final state is ground. Previously, we had the flipped role. We had the M squeezed between G and E from right and left respectively, and therefore a minus delta E was coming about. This time a plus iota delta E is running. So what we have to do, we have to write down the 2-point function of the field in the excited state 1k0 and then put it over here to undergo the integral to obtain the down transition probability. The 2-point function in the ground state was already known, in the vacuum was already known. Even for the 1k0 state, we had computed it before in the last week. You can go back to the last week exercise or even the last lectures exercise if you can look at. There you can verify we had obtained this expression for the 2-point function of the field. This first term was just the vacuum part, if you recall, times the normalization of state, because you recall 1k0 state is not normalized to unity, but it is normalized to the 3-dimensional delta function in the k space with the value 0. And the 2 remaining terms are coming from the state being non-vacuum. Okay. Collectively, you can employ the delta functions in the integrals. I have a double integral of d3k1 and d3k2 with the various delta functions appearing here and there, and you can verify. This we have done before. We should not have any problem in verifying this, that I would have an expression at the end of the day in terms of this vacuum term, which is a running k integral with plane wave structure at hand and a normalization of the state, plus 2 terms which are state dependent correction. There are 2 terms which are all complex conjugates of each other, and they do know about the frequency k0 at which the field is having the photon. The initial state of the field is not vacuous but an excited state at frequency k0. This information goes into the 2 extra terms which come in the 2-point function. The first term does not care about k0. This term is independent of k0. This is just a vacuum structure. On top of vacuum structure, there is a state dependent correction, which are these 2 terms. So therefore, these 2 terms will go and sit at the appropriate place in this integral over here, and we will get the total down transition probability. We have done this exercise before for absorption. This time the same integral has to be repeated again, only changes this exponential's argument is plus delta E. Now by now we are too accustomed to do all these integrals. So we do it piece by piece. First term is the vacuum term over here. This goes and sits over here. We perform the time integrals by collecting all the t parts and t prime parts at one place, undergoing the transitions integrals, and I get this as a result. This is the vacuum part and times the normalization of the state. This is coming from the first term over here. The second term will also undergo the same process and we will get this term. And the third correction term, which is over here, will sit in the appropriate integral over here and give rise to this term. Remember, all the time we are computing the things for atoms at rest. Therefore, whether in this or in this or in that, only the temporal part survives. The spatial x minus x prime is 0 for any time because atom is at rest. It is not moving. So at any time, x is going to be the same. So x and x prime, the spatial locations of that are going to be the same. They will drop out from the exponential and only temporal part will survive, which is undergoing the integral. And therefore, we have these states. Okay. This is for finite time. If I want to do for a long time value of the probability of transition, then I enhance the integrals limit from 0 to really large t, which is approximately infinity, but not quite, as we have discussed so many times. It is an operational infinity. That means much larger than the internal time scales, but smaller than the perturbation theory's breakout time. And then I divide the whole probability by the normalization of the in state. Remember, the initial state was not properly normalized. So one good way of getting probability is to divide the whole probability process by the normalization. So this integral over here converts itself into the delta function square, as we have seen. And these 2 integrals over here also convert themselves into delta functions. Actually, this iota delta E minus omega k0 becomes the third term, and this becomes the second term. So all 3 of them becomes delta functions of their arguments in the exponential. Only thing is that the first term is running with the k integration. This is the vacuum part. It does not care about where the field is excited. This is just the spontaneous emission part we have just seen. while these two remaining terms are the state dependent correction. It talks about whether or not the field is excited at appropriate frequency. Omega k naught is the frequency at which the photon is present in the field. Second term, you can see already it has a positive argument in the delta function, so it is going to drop out. Only the first and the third term are going to survive. I have divided the whole expression by delta 30, so this delta 30 will be killed off by this delta 30 in the first term, and the delta square integral will just become delta E upon h bar times delta 0. So I have missed out 2 omega k most likely over here, so 2 omega k should have been here, which converts itself into delta E upon h bar. Remember, this is the spontaneous emission process which we are talking about. This 4 pi k squared dk divided by 2 omega k gave me this linear frequency proportionality. So this is just the vacuum part. This third term which survives over here is the new part, which is, this is product of our delta function. Again, you do the splitting as we have discussed before. Use one of the delta function as delta 0, and then the remaining term is this. So this is again asking whether the photon is coming with the appropriate frequency or not. If the excited state of the field has a different frequency, this delta function dies down. But if it so happens that omega k naught is the same value as delta E upon h bar, the third term will survive and it will contribute this much to the down transition process. This delta 0 is coming from the square of this. Two delta functions in square are appearing. Delta x whole square is equal to delta x times delta 0. So that's how we have written these two things, and this division by delta 30 is coming from the state normalization. So you see that there are two terms which are causing the down transition if the field is already excited. First is the vacuum part, which anyway comes. This does not care about whether the field is excited or not. This is the vacuum spontaneous emission, plus this time a state dependence, photon dependent correction term, which is the stimulated emission. So you see the total down transition probability is vacuum plus the stimulated part. So there is a vacuum fluctuation which is also causing the down transition, and then there is an active photons presence at frequency k naught, which is same as delta E upon h bar. If that happens, then also this gets down transitions, and as a result, you get two photons out. One was initial photon which was sent in, and one was due to down transition the atom emits. If there is no time initial photon is sent in, then also the vacuum fluctuation causes it to undergo a transition, photon will be emitted. So in spontaneous emission, you send in nothing but a photon is obtained. In stimulated emission, you send one photon in but get two photons out. One last thing one should be careful about is this. If you look at this expression, forget about the vacuum part. You will realize it is the same expression which you obtained for absorption probability. It had to match the frequency and the coefficients are exactly the same. So stimulated emission part, not the spontaneous plus stimulated, only the stimulated emission part probability is the same as the absorption probability. So whatever is happening due to presence of photon happens with equal probability from up to down and down to up. They are just symmetric things. Only extra contribution comes from the vacuum part. Vacuum part was absent for absorption, but it turns alive for emission. So spontaneous emission assists the down transition. Up transition is only possible if a photon is there. Down transitions have both the things. Even if a photon is present, then it will down transition, then the probability are the same. But in addition, there are vacuum fluctuations which also cause the down transition. So only looking at stimulated part, one can ascertain that it is equal to absorption part as well. So this is just a nice figurative summary of the process. Absorption is only possible if there is an active photon present in the field. Emission, on the other hand, is assisted by vacuum fluctuation as well as the presence of the photon. Okay. Now these rates which we have computed for spontaneous emission, the rate was proportional to delta E upon h bar for scalar field, or it was proportional to delta E upon h bar to the power 3 for electromagnetic field. And this is the same probability which is the stimulated emission probability or absorption probability, and divided by the delta 0, which is the operational time capital T. If I divide by delta 0, the remaining term will be giving me the rate. So there are three rates in the game. One is the spontaneous emission rate, absorption rate, and stimulated emission rate. So these are sometimes called the Einstein's coefficients in the process. A21 is the spontaneous emission rate. It takes the state 2, excited state, to the ground state 1. Absorption, which takes you from 1 to 2, and then with stimulated emission, which is B2 to 1. It so happens that B12 and B21 should be the same as we have seen, but anyway, so total up transition rate can be given in terms of B12. Absorption will happen with this rate. It will be proportional to how many atoms are in there in the ground state, N1, and what is the frequency of the photon present. It should be directly proportional of the density of the photons present. So this is the total up transition rate. Total down transition rate is this B21. B21 is taking you down from 2 to 1, and it will be proportional to how many states atoms are there in the excited state, N2, and again the number density of photons surrounding this atom. But in addition to this stimulated emission, there is A21. A21 is spontaneous emission rate. This will also care about how many atoms are present in the excited state. If there are no excited state atoms present, there will be no down transition. But it will be independent of photons density, because this is happening due to vacuum. It does not require a photon to be present in the game. So therefore, the first term in the down transition is insensitive to presence of rho. Rho means the density of photons. But in absorption as well as in stimulated emission part, these two terms will be present. Most of the times when an atom attains an equilibrium under this up transition, down transition kind of thing, we do get this kind of detailed equilibrium condition that total up transition rate and total down transition rate should balance each other. This and that should balance each other. Okay. So we have just computed one case where the down transition, up transitions are all mediated by a monopole operator for our case, or dipole operator for electromagnetic field, or electric field rather. For magnetic field, it could have been a S dot B kind of term. So those kind of terms decide you what would be the spontaneous emission rate, what would be the stimulated emission rate, what would be the equilibrium condition corresponding to that, and this equation has to be satisfied for detailed equilibrium. So this is by and large most of the atomic discussions in atom-light interactions people do about, and try to see the transition probabilities of this with the interaction of light or background field, which we had covered. In the next set of lectures, we will see artifacts of this transition. So you see that there is a probability of transition caused by the electromagnetic or any background quantum fields. Now we will see in the next lecture onwards what other quantum properties are switched on due to this interaction. You see that even due to vacuum, that there is a probability of atom going to down state. For finite time operation, there was a non-zero but small probability of going it up as well. But large time, there is no up transition probability. It becomes a delta function of positive argument from being a sign function. So therefore, on its own, atoms are supposed to do this transitions due to the vacuum nature of the fluctuation nature of the quantum field. That means if I take many atoms, some of them will definitely undergo one of these transitions. So as a collection, what is the ensemble property of a collection will be heavily dependent upon what kind of field is surrounding that. And therefore, overall, how many atoms remain in one phase, how many atoms become a different phase. By phase, I mean which state they are initially starting with and which state they ultimately end up with. So in a collection, what happens? What is the global collective properties? If there is an entanglement between atoms, what happens to that? If there are corresponding properties between the atoms which are initially set up, how do they behave in the light of the presence of the background field? That we will start to see in the next lecture on this. So I stop over here, and then we will move on to look at other properties which we can infer out of it.